Hmm. Hello, Gordon.
Well,
How did the homework go?
I thought it was okay.
Okay, that's good to know. Hello, Jeremy.
Hello.
Liz, how was the homework? Any comments on?
I thought it was.
Yeah,
I
go
thought
ahead.
it was good. Yeah, I didn't have any problems with that. I thought.
Okay. Okay, good to know that. Hopefully that was the same for everyone. And let's homework 10 posted. Oh no, I haven't posted yet. Sorry, I have posted this. Yeah. And it will be due on 19th. And remember, our final exam. It's on May 3rd, Monday. We talked about time dependence or the complete Maxwell's equations and not just working in statics. And this leads us directly to what is called, what is broadly termed as radiation. And one message you want to take home from here is that whenever a charge is accelerating, it radiates. It basically emits light. You can ask, how do we get a radio signal? How do we communicate in general, or how is light generated? And anytime a charge accelerates, the conclusion is that it will always emit radiation. Radiation could be any electromagnetic wave. It doesn't just have to be light, but radio wave, gamma ray, everything falls in that category. And as we saw, our equations are reasonably complicated. Even for uniform motion, we have to struggle a good bit. But what we will talk about is mostly when an observation point and a source, observation point and source point are relatively far away. And in those situations, our equations will significantly simplify, and it allows us to proceed or analyze quite a bit. So broadly, we will call this radiation. And today we will talk about radiation potentials. Like usual, we will first get the potential in the so-called radiation approximation. It's an approximation in the sense that it is not a complete solution, but nevertheless, in that particular regime, it is reasonably exact also. So we will call radiation potentials today. And next time, in the next class, we will come and evaluate the fields. And in general, we would like to have an expression for what is the radiation due to a point charge. What I've suggested is that whenever it accelerates, it radiates, and we would like to know how much energy is emitted in a certain direction or of certain frequency and so on. Like if you accelerate at a certain speed, what's the expectation? What kind of frequency can you emit? So that's our goal. Our equations, remember, are for the potentials. We have the wave equation. And the source is the charge density. Now, it can also have a time dependence. We showed that these equations in general can be written in terms of what we say is an electric potential due to a point charge at an instant. Let us say if it were to have a source just at one instant and you were to observe it at another time, what is the contribution due to that kind of a source? That was the Green's function. And we showed that the Green's function has the form t minus t prime minus, this was retarded, right? The time at which you observe is not just separated by t prime, it is actually also separated by the amount of time light takes to travel that distance, the distance between the observer and the source. Okay. And using this, we can immediately, since these differential equations are linear and the sources, it is equivalent to adding up all the sources separately, or the contribution from all the sources separately. So we say that our potential at any time is equal to the not only the superposition of sources at every point, at every time also. we evaluate this from dt prime. So t prime goes from minus infinity to plus infinity, and at each point in space if the source exists. So that's 4 pi r minus r prime. I'm leaving some space here. Pretend if this was static, then you would have just set this like rho r prime, comma t prime. But there is a contribution from the time part, and that's of this form. And that's your extra piece, that delta function. And one would have worried that, oh, we are integrating from the source point or source time, if you want, at what times did the source emit, going from all the way from minus infinity to plus infinity. You would worry that, oh, that's not okay, because you're including future times. But this delta function makes sure that the future times do not get any contributions, because t prime is t minus a magnitude of quantity, so it is always always causal. Same thing for A for completeness. Oops. So and it's mu naught over 4 pi pretty much the same as earlier. The difference is that there is t primes in the sources, and there is a delta function, which is defined in terms of what is called retarded time. So let me change the pen. Notice whenever, since we are integrating on t prime, we want to evaluate when does this argument go to 0, and that happens whenever t prime is equal to t minus magnitude of r minus r prime. Oops, it's not visible. So this is t prime is equal to t minus so instead of the observation point being at t, it is you get a contribution from the amount of time it takes for the signal to go from the source to the charge, and this is called the retarded time. So this is retarded time. So it doesn't, you don't see the signal at t, but at a different time. So this is retarded. Or maybe I didn't say it correctly. Like this is if you had to imagine, typically you would have said this has to be evaluated at t prime, but you have to evaluate it at a point in the past for it to be able to travel that distance and get observed at the point t. Okay, so that's your potential, and that's what we want to evaluate. And as I suggested, that this is too complicated a problem. Like even for a uniformly moving charge, a charge moving with uniform velocity, we tried to do this exactly, and it got very complicated very quickly, and we saw that we encountered a quadratic equation in here. If it was accelerating very quickly, this becomes very difficult to track, or you can say impossible to track. So we want to work in some regime, and that's what we will call the radiation. We want to define radiation at this point. So let's consider two scenarios. So case one is when the time, so t minus t prime that we have is very much greater than r minus r prime over c. So there is a source point and there is an observation point, and there is a time for which things happen. So for example, the picture that's possible is that, so r prime typically is associated with the sources, and they are usually confined in space. For example, it could be in your laboratory or it could be on Earth, and you make the observation very far away. So that's one possibility. Or it could be that the observations are made very close by. But now, what do you mean by observations are made far away or close by? There has to be a reference position for that. There has to be a reference distance. When you're in atomic physics, you would say r minus r prime is the distance between the observation point, which is in the lab itself, and the atom. But if you're in cosmological scales, you will say that observation point is between two stars, right? A star, light is emitted from a star and it is observed on Earth. So those are two different stars. And how do we compare what is small and what is big? For that, we have to talk about a reference time. How much time does the system evolve? For example, for an atomic physics problem, you would say how much time does it take for the atom to go around, like the electron to go around. So there is usually a characteristic time of the atom itself. So let's call this a characteristic time. So let's call this tau, and this will be a characteristic time. And since we are talking very general terms here, so we don't want to specify what exactly is that time, but it is some time scale that decides the system. And if that is very large, then you can neglect this term. If this is very large, and by large we mean it has to do with accuracy. If you want 10%, you say it is 10 times larger. If you want 1% accuracy, you say it is 100 times larger, and so on. And in atomic physics, this comes out to be a million or more, a billion times larger. So that's a very good approximation. And the same thing in cosmological terms also. In that context, notice what happens, that this can be neglected and immediately the time integral can be done. And we will see that that's a static limit. We'll talk about the situation very quickly. But before I do that, let me talk about the second situation, which is what we will say is the radiation approximation. And in that case, this is very much less than r minus r prime. Notice this is not just saying that r is larger than r prime, which is what usually that's what happens, that r is significantly larger than r prime. But r prime, if you choose it at the origin, then we are basically saying that there has to be a time. So there has to be a time scale we have to compare it with. In atomic scales, it will be the frequency of, for example, frequency of light that is emitted, right? That's also a scale. Okay. Let's, before we proceed into radiation, and this is what we will call radiation. In general, this extreme limit. And this actually, even though it is not obvious, I'll show this in a minute. This is basically statics, right? We are pretty much doing statics, even though there is time dependence in there, but the time dependence is just innocent. It doesn't actually contribute significantly. So how does that work? So let's see that. So let's do case one first. And we are saying t minus t prime is very much less than or minus of 1 over c. So I can neglect this, right? So this will be neglected whenever it comes in. So phi or t is equal to 1 over 4 pi epsilon naught. At integrate over t prime, it's t cube of prime, and I have delta function t minus t prime minus r prime over c. But this is small. Oh, I have to say the opposite, right? Oops. I meant the opposite. The case one was larger. So this is significantly larger. So I can neglect that, relatively speaking. That's 4 pi. Oh, no, not 4 pi. Oh, I think I messed up here. It's a small mistake. So when I wrote these expressions here, I wrote the 4 pi double 2 times. So get rid of 4 pi here. 4 pi, 4 pi. So get rid of that. And here, similarly, so this is r minus r prime. And I have rho of r prime, comma, t prime. Once I neglect this, it is easy to do this, evaluate this integral. Again, recall when we were doing this for uniform charge, to evaluate that integral was a little work. We had to actually get the contribution, or at what points t primes does it contribute, so decided by a quadratic equation. In this case, it is linear. Immediately do the integral, t prime gets replaced with t, and it's leads to cube r prime and rho of r prime. Now t prime is replaced with t, and we have r minus r prime. Notice what has happened. That's exactly like statics, except that there is charge time dependence in here, but the time dependence is completely innocent. Whatever is the static contribution, you just change it. If the charge is moving, it pretends as if it is static, except that, yeah, it is moving, but it is always r minus r prime that is contributed. So this is practically statics. Even though there is time dependence, it's an instantaneous time dependence in the sense. Action at a distance, whatever happens here, immediately everyone in the galaxy or everyone in the universe knows that you did something. Signal travels at infinite speed. And the same thing for the vector potential. So the vector potential is r comma t is mu naught over 4 pi and we have current density of prime t now. So notice t same as what we had for electric potential. So everything happens like statics. There is instantaneous communication between one point to the other. But that's not what we are interested in. We want a radiation scenario where the distances traveled are significantly larger than the characteristic time of the system. So let's do the opposite scenario where, so we want to talk about case 2, which is radiation. And And
Could you scroll up just a little bit for that last equation?
oops, it's not visible. Oh, yeah. I think it's not visible maybe.
Yeah, I just need to see A.
Okay, good.
Thank you. Okay, I'm good.
So, so the primary thing is that there is this distance scale and there is a time scale. And we know that this distance is a magnitude of a quantity. If it is at the origin, it is very easy to work with, but typically it is not at the origin. So let's see how we can process that distance and make some approximations in it. Remember here, we do a series expansion in these matters, right? So let's talk about the distance r minus r prime, which is the magnitude of a square, right? So square root of a squared quantity. That's, we have done this before also. And this is r square plus r prime square. And then there is minus 2 times the vector r prime, r times r prime, and the square root. That's exact as of now. Let me do this point. Let me take out this r in here. And this is 1 plus r prime over r the whole square minus of 2 times vector r over r dotted with r prime over r. Now this will be called a far field approximation. So this is an additional approximation we are putting in, but most of the time it will turn out that radiation or many of the interesting problems will be involving the case where the observation point is significantly larger compared to I will be able to choose r prime to be 0 and r is significantly large. So r prime over r, this is in that case the second order can be neglected. So this is a smaller quantity related to this. Notice that this is an observation or what we are going to neglect is r prime over r square is, or this is significantly less than 1. That's what we want to talk about. And in that case, I do a Taylor expansion of this binomial structure. So there's a square root of half. So this is first of all neglected. So this doesn't exist. So there's only 2 pieces there. And then I do a Taylor expansion of that binomial expansion. So that's 1 minus of 1/2 of 2 times vector r over r dotted with r prime. And these are higher order terms. And this is factor of 2 cancels out. These are the 2 terms comes in. So this is equal to, I expand this or put this in again. So this is minus of r hat dotted with r prime. Vector r divided by r is r hat. So that will be our approximation. So we will be using r minus r prime. We will be replacing it with r minus vector r dot with r. And we have to be careful. We have to always compare it with the characteristic time, right? So this is the distance. Whenever we have neglected this, so basically we have said that this is smaller than, or this is t minus t prime. When you compare it with, you're actually not keeping it. We cannot drop t minus t prime completely because we have a delta function sitting there. We have to evaluate it at that time. So that we have to keep that. We have to do one more approximation. And that is because it is in the denominator also, right? So that it is showing up in the denominator also. So it's r minus r prime. And that's equivalent to saying this is 1 over r. And if you go by the previous step, it's r prime over r. One would expect that one has to keep the second order also here, but whenever you already have an r, you're beginning your denominator with a factor of r. That means when you move it to the numerator, you don't need to keep all the orders. In the leading order, you just need this 1 over r. So it will turn out that this is it is sufficient to keep 1 over r. Because remember, we are only interested in the leading order approximation, and for getting the leading order approximation, we don't need to keep this. It will be the next term, which we won't worry about. So with these 2 approximations, which will be playing an important role in radiation potentials, let's see what our electric potential is. 5 RT, that's 1 over 4 pi epsilon naught dt prime d cube r prime, and we have delta function of t minus t prime minus, this time we would say this is r over c minus, but there's a minus and a minus, so it's plus r hat dotted with r prime over c. So we have changed this factor here. Divided by r minus r prime, I just replace it with r. That's a simple, significant simplification to the extent that there is no r prime now. I can move this out. I can move this out of the integral completely, and we also have rho of r prime t prime. Okay, so this was simplified. So what are the quantities that were simplified? This quantity was replaced, and with the negative sign, let's say this quantity here was replaced. Both the boxed quantities are not exact anymore, so that's the approximation that's involved. At this point, t prime integral can be done, or let me write one more step. So this is 1 over 4 pi epsilon naught. It is 1 over R completely comes out. There is no R prime dependence here, so significantly simpler. And I should say that this is with the far field approximation. So this is radiation with the far field approximation. And that is, and let me also interchange this dq prime, dq prime, and dq prime. So that I can actually do this integral. Let me define this to be TR minus T prime. So, and this is rho of R prime, T prime. So what did I do? So this is visible. Yeah, so this is visible. Let me define retarded time as T minus R over C plus R hat divided with R prime over C. So the retarded time has been approximated. This can be integrated out. So T prime, that is no, so that is whenever T prime is evaluated, this can be immediately done, and that's equal to 1 over 4 pi epsilon naught, 1 over R, oops, and G cube R prime, and charge density. There's just a charge density that you're integrating upon. It should be the total charge in general, but this is evaluated at different times now. So this is T prime gets replaced with T of R. Let me explicitly write that. So this is T of R plus R hat divided with like one might argue that, oh, this should be the total charge. No, because there is an R prime dependence in here, right? The time is not unique for every R prime. So you cannot just say that you conclude that this is actually the total charge. In general, the integral of a charge density should give you the total charge in that volume or in that space. But in this case, it is not, because it depends for each R prime, your time is different. In that sense, it is not really a total charge. So that will be our expression for electric potential in this extreme limit, which we will say is the radiation in the far field approximation. And similarly, we can also evaluate the electric potential. Magnetic potential will be the same thing will go through, and what we will get is mu naught over 4 pi over R. And this is E cube prime. This is J prime. T is R over C plus R hat R prime over C. And the primary difference again here is the R prime dependence that shows up here. And one has to be careful as to which terms to keep and which terms not to keep if you're actually evaluating the fields. So let's, so these are your electric potentials, and often these are called, I think, oh, I don't remember the spelling. I think it is Leonard. Spelling. Which potentials? Oh, we have a computer here, right? I don't want to write the. Yeah, Leonard which W-I-E-C-H is a called Leonard Wishart potentials. Okay, so that's your potentials. It's not very intuitive because the retarded time is pretty convoluted with respect to R prime. So not immediately very intuitive, but let's actually try to get the fields. And it will take some effort because now what's the challenge that comes in? Remember that electric field is negative gradient of the potential minus the time derivative of the vector potential with time. And the magnetic field is the curl of the vector potential. The major challenge that comes up is that whenever you're taking the gradient, it's not just your not just your R that it is sitting, it also hits your R here, and there is a R hat, right? So it hits this also. Right? So you have to hit at all these points, and then you have to calibrate it with whatever we have already thrown off. So we have already made an approximation. So you have to be consistent with that approximation. So if it is higher order contributions that you're getting, so you have to drop that out. So to that end, and since we don't have too much time remaining, so I will do one piece of that calculation, which will be needed next time, and we will go from there. Remember here, let's define the retarded time as T minus R over C plus R hat dot with vector R prime over C. That's your retarded time. Whenever we take a gradient, I have to hit the explicit R dependence, and I have to hit any R dependence inside this. So let's see. So let me evaluate the gradient of the retarded time. Why am I doing this again? Because I will be taking the gradient of the potential, and when I take the gradient of the potential, since the potential has a dependence in retarded time, the gradient will see this functional dependence. So for once and all, I try to evaluate this. Gradient does not depend on time, so that's 0 minus 1 over C, and that is gradient of magnitude of vector R plus, let me write this as gradient of R hat, which is vector R over R, dotted with R prime over C. Notice this dot is on the right side vector, not on the gradient. So gradient is a free vector. Gradient of R we know is R hat. We've done this many times, so it's R hat. So this is minus R hat over C plus, what's this equal to? Again, this we have done a few times. So this is equal to gradient of vector R is equal to the dialectic, unit dialectic. So it's unit dialectic over the magnitude R dotted with R. Let me do this first. So this is minus of gradient of R, which is minus 1 over R square and R hat. So R hat over R square times times vector R. over C. Open this up. This is minus R hat over C. In the workspace, yes. Let me keep 1 over C all the way in the front. In fact, I can keep 1 over R square, right? So let's put an R square out. And 1 over C also out. So what we get is I put an R times R hat. Is that correct? How should I write this? So let me put an R cube out. R cube out. So this will be, I'm providing an R square in here times vector R prime. Minus, since I put an R cube, so I can provide an R in there. So that's vector R dotted with R prime. And a little observation of that quantity in brackets will show you that, oh, that's actually a cross product or a double cross product. So that's equal to, oops, I think I should be out of the board now. So that's equal to minus R hat over C plus. What is this equal to? So let's keep this as 1 over R cube. And notice what is this vector equal to? So that's R prime crossed with vector R. And then you cross it again with vector R. So probably this is what it is. So let's check. So the first one should be R prime. So that's R prime and then R dotted with R. That's the back cab rule, right? So that's R square minus vector R, and then you dot with these two. So that's exactly this. Let's rewrite this slightly because it's a unit vector. Each one I can provide a R prime. So this is minus R hat over C. And let me write this as minus of, so that I can write the R prime onto the extreme right. So this is R hat crossed with R hat crossed with R prime, vector R prime over R. And that is a 1 over C. So that's a total expression. We will need this next time when we start thinking, evaluating the fields. So again, we need to, so what's the idea here? So we have gradient, you have to take the gradient of the electric potential, which has dependence in the retarded time, and that will require this gradient of the retarded time. So remember, so this is gradient of 1 over 4 pi epsilon naught, 1 over R, and I have E cube, R prime, rho of R prime, comma, T of R. So how does this gradient operate? So gradient will first operate on this R. So this can act on this, or it can act on any R that is there inside this retarded time. This is all R prime. I don't care for R primes. The gradient will see only the R dependence. So we evaluated the gradient of T of R, but then I have to use a chain rule. So first get the time derivative and then get the T of R out. And we'll do that next time. We have the potentials today, which went reasonably straightforward, but the electric field will involve a little bit of manipulating so that we get all the right order terms. We are collecting and dropping all the higher order terms. And then we will be ready to analyze what is the radiation in the far field approximation. That is all, and I'll stop here. Thank you.
See you next time.
Gordon, any questions?
No, I just finished writing this stuff down. All right. Have a good day.
You too. Take
Thank
care.
you.
Mhm.